Thank you very much for the invitation. So I'm going to start with the statement, even though maybe you know what it's about, but and some reductions. So the conservativity conjecture says the following. So I restrict to Chow motives today, and K will be always my base field, which will be of characteristic 0, and I will be working rationally. All right, so the conjectures say the following, simply say that if you look at the Theorem cohomology and you think about this as a functor from Chow motives to graded vector spaces, then this functor is conservative. So in the sense that it is, it detects isomorphism between Chow motives. So concretely, it means that if you have a correspondence between Chow motives which acts on cohomology as an isomorphism, then this correspondence is invertible. So I will be as I said, focusing on Chow motive, but somehow everything I will be saying today will take place in the framework of Voivodski motives. So I remind you that we can think about the category of Chow motives as a subcategory of Voivodski's category Dm. So there's a fully faithful embedding like this, and moreover, the RAM cohomology is representable in this category. So the RAM cohomology. Oops, sorry. Dm, and in fact, it's representable by a very nice and simple object name, which I will be denoting today by omega underline, and it consists of the collection of the RAM complexes shifted by n. So this is a so-called T spectrum, and right. So this is, as every object in Dm, this is a T spectrum where my T, at least for the moment, will be simply the Tate motive. So E1 times tensor by Q, and here E1 is my notation for A1 minus 0. Right, so this is Gn pointed by 1, and you take the free sheaf on it, and this is the T, and this guy is a T spectrum. So the first thing I want to say today is how one use this object to reformulate this conjecture. This is very, very easy. It relies on the following lemma, which is a version. I mean, it's just Kunit formula, the Kunit formula, which say that if you take an object, take a motive in Dm, then the internal home from this object to the T spectrum that represents the RAM cohomology is very simply given by the RAM cohomology of the motive that you can define as a usual home, not the internal home, between m and omega, and tensored with omega. So this is tensor over K. And so this is really, if you think about it for 1 second, you see it's just a reformulation of the Kunit formula. And somebody is sick. Sorry? Sorry? Here? K, yeah. This K is the base is a coefficient field of the cohomology theorem. No, this the formula is like this. It's the RAM cohomology is contravariant, and so I use this for the following corollary. So saying that the RAM cohomology of a motive. So this is for M compact. So let's take M geometric. Then saying that the RAM cohomology of M is 0 is equivalent to say that M tensored with omega is 0. This is as an object in Dm. So this is again very simple. Saying that, so here I need duality. So saying that the RAM cohomology of M is 0 is equivalent to say that the RAM cohomology of the dual of M is 0. And this is where I use geometric duality. And but then using this previous lemma, this is equivalent to say that the internal home from M dual to omega is 0. But this is again by duality. This is simply M tensor omega. Okay, so because of this simple lemma, so we are led somehow to consider the following definition. So let's say, so let A be an algebra in Dm. For example, A could be omega, and I would say that A is tensor conservative on Chow motive, and sometimes I'll just forget about precising that I'm thinking about Chow motive. So we say that A is tensor conservative if simply the tensor product with A, which is a functor from Chow to Dm, is conservative. Alright, so we are so the goal is to show that omega is tensor conservative in this sense. All right. So what is the reason for introducing this definition? It's because there are natural examples, A, for which one can show more or less easily that they are conservative. And so I will make a proposition, give you some condition which implies that an algebra is conservative. Let's run like this. So here's a proposition. So let A be an algebra, and I write this as a spectrum. Right? So it consists of sequence of pre-sheaves on smooth varieties, AN, be an algebra in Dm. I assume that A is fibrant, but so A assumed also stably fibrant, which means that it's an omega spectrum and so on. And let's assume the following two conditions. So assume first that A is -1 connected, which essentially mean that the pre-sheaves or the sheaves AN they have no homology in negative degrees. So, and here homology is taken in the sense of sheaves, right? So if you sheavify if you look at the H minus something, you sheavify for the type topology or for the Zariski topology or anything, then this should be 0. This is -1 connected. And the second condition is that it's something about the A0. Assume that the A0 is constant. So so you have some coefficient field lambda. So let's say lambda over Q and a field extension. And you assume that your spectrum in degree 0, so in level 0, is given by the constant pre-sheaf lambda. Then the conclusion is that is tensor conservative. And the proof is rather easy, so maybe I sketched. So it relies on a version of Bloch's formula, which will give us the following fact. So this Bloch's formula in the setting will tell us that if X is smooth for IT over K, then there exists a surjection from the Chow group of X. Maybe you extend the scalar to lambda. So this will surject to something that I denote by CH in A of X, and this is by definition just homomorphism dm from the motive of X into A n to n, as you might expect, right? So you think about A as a cohomology theory, and it gives you some kind of Chow groups, and so these two conditions would tell you that there is a surjection like this, which is and that guy will also surject to the same thing, but for the algebraic equivalence. Right, so this is very simple. You just write down essentially the Gersten complex, and at the end of the Gersten complex, you will have direct sum over the point of codimension n because of this condition. And then you have to analyze the first differential, and you can do it, and there is such a form. So maybe I end the proof here. So once you have this, maybe I put it here. So once you have this, have remarked this, then you can deduce that. So there is So saying that M tensor A is 0 for a Chow motive would imply that that homomorphism from any Chow motive to M will be 0 algebraically. Essentially by using that this guy here, this can be written as hom in dm between n and M tensor A, using duality and so on. And so M tensor A0 would tell you that. And if this is true, then for any n, then by Yoneda lemma, that means that M is 0 as the motive is algebraic, for the algebraic equivalence. But then we know that by the nilpotence theorem of Voevodsky that necessarily M should be 0 itself. Okay? So this is the basic idea is to try to use this simple fact to prove that omega is tensor conservative, but of course this is not really possible. So maybe here's a remark. So yeah, maybe the strategy is to relate omega to some to a T spectrum, to an algebra satisfying 1 and 2. Of course, I should maybe try to make this precise. What do I mean by relate? So of course, it cannot be a naive relation. So I mean, of course, here's a lemma which maybe gives a hint of what we are trying to do. So of course, if you have a morphism of algebras in DM, and if you know that B is tensor conservative, then of course A will be tensor conservative. This is very easy. So we could try to see if there is a map from omega to something which is tensor conservative or something satisfying this condition. But you see immediately this is too much to ask, because somehow, as you saw in the proof, any a in the proposition will somehow will see cycles will be somehow weaker than the algebraic equivalence on cycles, and in particular, so it's a theory which will give you groups of infinite ranks by Griffiths and so on, and so you cannot map omega to it, because then you would somehow get a factorization of the cycle map in the wrong direction in some sense. Okay, so it's not possible to go from omega to such thing. So one has to find maybe a more complicated relation. But here's one reasonable expectation. So here's a conjecture, and I explain why this is enough. So the conjecture is as follow: you take you consider the Hodge complex on omega. So this is you can think about it as a cosimplicial algebra, where you put in degree 0, you put your algebra omega, and then there are you tensor to itself, let's say over k, and so on. Right, so this is usual Hodge complex on omega, and so the conjecture would say that there exists a natural map of the following form: homotopy limit over delta of this guy. So this it will map to something that I denote by tau bigger than 0. So this is like we have seen in the first talk. It's like the connective spectrum, if you want to set it to omega. Right. So this is the conjecture, and of course it exists a map which will be we expect to be compatible with the units. Okay, not any map. Right. So maybe why this is enough? So remark. So this is enough to show that omega is tensor conservative because of the following remark. So here's the proof: if omega tensor m is 0, this would imply, or this is even equivalent for m geometric to saying that Hom internal, let's say m or m dual, doesn't matter, is 0. Now, since internal Hom commute with homotopy limit, you see that it implies that the Hom intern of m dual tensor this homotopy limit is also 0. And from this, it's easy to finish, because once you have a map to that, you see that you can use that this is tensor conservative to conclude. And this is tensor conservative exactly because it fits in the previous proposition. Okay, so it's I mean, I should maybe write it. What is this guy? This is very simple. It is the following spectrum. Okay, so in particular, it clearly satisfies the conditions of the proposition, right? All right. So this is what I try to speak about today. This is this conjecture. Right, so just all right, so what is the plan for proving this? So we first say a few words. So maybe some general remarks. So we are looking for a map from a homotopy limit to something, and it's somehow, of course, it's a map from the wrong direction. It's usually difficult. So it's usually easy to find maps to some homotopy limit, but much more difficult to go to the other way. And moreover, homotopy limits. So I mean, of course, then somehow the idea would be really to understand completely this homotopy limit, try to compute it completely, and see if it goes to something. But somehow homotopy limits are very complicated. So in any reasonable homotopy setting, of course, homotopy limits are just opposite to colimits, but in any category which are of interest, homotopy limits is something that is hard to compute. So here's an example. I think. I mean, I don't know if it's. I think I've heard it once from Voivosky that you would expect that if you take the product of infinite product of Q0 in say in DM, then this will contain, in some sense, the motive of every variety. So it's one really has to be very careful when dealing with homotopy limits, or complicated things. But somehow, if you want maybe the slogan is that so a homotopy limit is very complicated, except if it has a reason for not being complicated. Or otherwise. So one has to find what is the reason for which. So if this, I mean, there is a stronger conjecture which really which says completely what this homotopy limit should be, and in fact it should be simply maybe something like Q. So the motivic homology tensor with K. So we do expect that the homotopy limit is a nice and simple object, but still to find why. So we need to somehow to find out why this homotopy limit is will be nice and computable. So and here's another remark which gives I mean, this is a very simple situation where we can indeed compute a similar homotopy limit, and this is as you probably have seen this before. If you're so let's start with an algebra, let's say in DM, and assume that that this A has a retraction, which means let's say goes to from A to Q0. So whenever you have such a, or whenever you are in this situation, then it's not difficult to see, or it's really very easy to see that the homotopy limit will be simply Q0. And this is again via an explicit argument. So you just look at you look at these complexes, and you look at the identity map, and you see that there is a homotopy, which is simply given by the retraction. Right? So here you take identity tensor, the retraction. And so this gives you tell you that this complex is homotopy 0, and therefore Q0 is equivalent to the homotopy limit. Right, so this is maybe an example where homotopy limits are simple because there is a reason for this. So we could try to look for retraction in our setting, and see if one can somehow try to repeat such an argument, or a variant maybe of it. But of course, again, this phase very essentially for again this maybe the same reason. So again, remark omega, of course, has no retraction, to Q. Again, simply you cannot go back from Chow groups to, so the cycle map has no retraction for obvious reason. So this will not work, but there is so this is a negative result, but there is a positive result. Namely, if you look at level 0, so what do we get? We remember it's simply given. So the spectrum is given at each level by the de Rham complex shifted by n. So in level 0, it's just the de Rham complex. And the de Rham complex has a retraction. So the unit of k has retraction. But it's not an obvious one. In fact, this fact uses the theory of weights. So I sketch again the argument, but really very quickly. So the point is that there exists a weight filtration on omega. It's not any obvious filtration on omega. It's not really a filtration on the complex. It's just a filtration in the derived categories. It's nothing really that you can write down, but it exists by Deligne, and so on. And then, and even more, because it's a weight filtration, there is an isomorphism between this and the graded pieces. And therefore, you can project to the group 0. And then, so this is okay. And then by what we know about the weights, we know that this is really very simple. This is simply k constant as a pre-sheaf. And so this is how you get your retraction. It's really, I have to say it again, it's not any easy construction. It's something that is, it exists, but we don't really know how it works in some sense. So this is, I would consider this as a negative. So this is a negative fact, and this is maybe somehow positive. But, and so somehow we will try to use things of this kind somehow to do what you want to do. So but it's not a filtration on omega. You have a filtration in the sense of, so what really happens is that there is a complex which happened to be quasi-isomorphic to omega by a zigzag, which is canonical and functorial, and on this complex there is an actual filtration where you can take the graded. It's very easy. Should I say it? So this is a map in the derived category of sheaves on smooth varieties. Okay, it's not a map of actual complexes. So I'm saying that there is a map in the derived category of sheaves from the de Rham complex to the constant one. But you cannot write it down. It's really, it exists, but it's a splitting of again, up to homotopy. I can tell you how this is constructed. You will see it immediately if you want. Maybe it takes less time than just discussing this. So So you use the construction of Norrie and maybe Beilinson, which gives, so you know this construction. It's you take your variety X and you try to filter X by codimension 1 and so on. And then you get a complex, which, so you get a complex of int mixed Hodge structure, computing the Theorem complex, which is isomorphic to the Theorem complex. And you use that complex, and you have a weight filtration on that complex, and so on. Okay? This is how it works. Sorry? It's an isomorphism here. It's also here. Everything is here. I mean, there is an isomorphism between omega and this complex of mixed Hodge structure. I mean, of course, you forget about the structure. I don't know. Should I? Can I continue? All right. So, okay. So, this is effective. So, I don't know. But what do you want? Okay, I'll do the proof. Sorry, I will not finish. So proof. So I claim that given X, you can find, so there exists a functor, which let's call it C Hodge. It goes from smooth varieties to end complexes of end mixed Hodge structure. Do you agree with this? And that guy computes the Theorem cohomology in the sense that the sense that there is a zigzag between this complex and that complex. Do you agree with this? All right. Now that complex has a weight filtration, so I could project to the Greuze. It's effective. It's a complex of effective mixed Hodge structure, so it projects to the Greuze 0 of it. Okay, which I claim that this is quasi-isomorphic. There is a natural map from K. So what I do is so to be precise, I should say you forget. So you take the fiber functor Theorem, apply to this, and this is quasi-isomorphic to that. Okay, now you have that f Theorem of the Greuze 0, and this is simply K constant. Okay, so these are quasi-isomorphism, and this is the map. Okay. Greuze 0, weight 0, Artin. So it's an effective Hodge structure. So Greuze 0 means that the filtration is there is no filtration, nothing. There is just it's a weight filtration. It's increasing. Weight filtration. No, the smallest one. W0 is the smallest one. Yes. Otherwise, I mean, if it was the largest one, then I would not need to do anything. I just project to it. This is the point. It's the smallest one, and you need to split the filtration. What? I'm not saying that there is splitting, and I'm not saying that the mixed Hodge structure is split. I'm not saying this. I'm saying, I mean, right. If you take H and mixed Hodge structure, I'm saying that there is an isomorphism between H and the GRU W0. I'm not saying it's a canonical one, but it's a functorial one. So this is a Tannakian formalism. You know, it's from the linear, the Hodge, maybe 2 or 3. It exists maybe over K bar. I mean, I will use it later. Actually, maybe you can, but it's really. So I'm saying that the RAM component of your mixed Hodge structure, you forgot about all the structures. The RAM component has the weight filtration has a splitting, which depends on something. I mean, it's not a canonical one. Maybe, yeah. So there is a construction. What? Yeah. I mean, it's functorial in Hodge structure. Yeah. I mean, we will never finish on that one. So I okay. So yeah. So what is let's see. The idea is to to use again. So to use weights on really on omega the spectrum. So this is what we try to do, and then use this to somehow to mimic the proposition or the lemma I just erased. Okay, so I mean there are weights on this guy. In fact, there exists a weight exactly as before. Exists a weight filtration. Well, again, omega on the whole T spectrum, except that it is it's not effective anymore. So, but not effective. And this is easily seen if you look at. I mean, this has to do with the bounding map, with the assembly map. The assembly maps are going. So let's say from level 0 to level 1, it's a map. So, like that. Maybe it was 1, I think. All right, so it's given. It's a map like this, and it's a map which is given by coupling with the canonical class on E1. But the problem is that this class is not of weight 0. It has weight 2. Okay, so what to get a weight filtration on this guy, you will have to so it will be something like that, or maybe let me just write the graded. Oops, the graded objects to weight filtration. It will be so in degree let's say 0 simply. It will be given by GRU W2n, the complex shifted by. So you are forced somehow to look at higher weights depending on the level, and because of that, somehow you cannot you don't get a retraction of the identity map of the unit map, but you get a map to this object, which is still very complicated. And in fact, proving the conservativity for that object or for omega is really equivalent. So we don't really gain anything by doing this. So we have to look for a different kind of weight and somehow. So we need to get weight from a different source. And so it will be important for me to get a weight filtration which is still effective. So I don't want to. As I said, the the weight filtration on omega underline is not effective. So it has negative weights, and this is not very good for what you want to do. So we try to get a filtration which is effective, namely that its W minus 1 is 0. So, right. So the source is the following. The source of this new filtration will be the following theorem. So I'll state a statement and then explain this, what it means. Some of you have already seen it before, so but maybe not all of you. So the theorem is the following: there exists an isomorphism in DMK between the following two objects. So the first one is it's so-called P1 delta localization of the infinite T suspension of a complex, which has very much to do with the RAM complexes, and I'll explain in a moment what it is. And then you have to restrict this guy to smooth varieties, and this is the thing that you are interested in. So here are some explanation. So the right-hand side is the restriction to smooth varieties of a T spectrum over a larger site, so-called the site of smooth foliation, so over SM all K. So which contains smooth varieties, and oh yeah, thank you. So an object of this smooth foliation category it's denoted like X over something, and this is given by a scheme X and a choice of a quotient of a sheaf of differentials. Okay, so it's you just change the omega 1 of X, you replace it by something smaller, and there is some condition like integrability that I will not write. But in particular, there is the RAM complex. So the omega F is the natural RAM complex on smooth foliation. Right, so the one that you get by using this instead of that. Okay. Then I think the remaining thing that I need to explain is what is log P1. Log P1 delta is similar to log A1, and you know what is log A1, so this is the A1 localization. So it's the same idea. You transform something into a theory which is P1 delta local. And what is P1 delta local? This is exactly again the same idea. Is that maybe put it here. Let's say a theory. Maybe so. I.e. pre-sheaf F is P1 delta local if when you evaluate f on p1 delta times something, it's just f of this something. Okay, and p1 delta is just p1 with zero differential, so it's considered as a discrete object in this set. Right. So I don't want to spend more time on this. I just so I want to explain to you what is the source of the wave filtration that I will use. So it's coming from this isomorphism. So I now try to somehow analyze it a little bit and tell you somehow what this thing gives. So yeah. So here's a remark. So this is a simplified interpretation of this theorem, which means that what I'm saying here is far from being correct, but it's just to give you an idea what's happening. So this theorem allows somehow to compute the ramp cohomology of x for some x in smooth varieties. So in an effective, let's see, how did I phrase this? Yeah. So, yeah. Sorry about this. Maybe I should. It's difficult for me to explain, so I just maybe write. So I prepared something, so I just use it here. So we get in this way, we get the formula for omega, which is effective. So in the sense of weights. Why it's effective? Because I mean, remember the failure of effectivity for omega was exactly because we had to choose a generator of the H1 Theorem of E, which does not have weight 0. So it forces us somehow to become non-effective on each level. On the other hand, so the left-hand side of this formula, there is no such choice. It's something which is completely effective in some sense. So, and so somehow, if you take a weight filtration on omega, it will just induce you a weight filtration. It's not as easy, but so the point is that there will be no weight filtration on omega f. But if we assume that there's a weight filtration on omega f, then we get automatically a weight filtration which is again effective on the left-hand side, because there is no need to change the weight filtration on each level. Okay, so yeah, its localization will be also done level-wise somehow. The P1 localization is also level-wise. It's very imprecise. It's not, but yeah, the idea is that one can think about the left-hand side as an effective object. So we have a formula for this non-effective guy, which is somehow effective in some sense, but what we lose is that it is in term of the RAM cohomology, but not necessarily now the RAM cohomology of varieties over K, but rather relative RAM cohomology. So things of this form. So let me explain why relative RAM cohomology appears in this formula. This is simply because of this P1 delta. So how one should think about this formula. So if you know, I mean, remember A1 localization is about, so or can be written as homotopy colimit of things of the form, let's say, of internal home an to something, right? So you start with your complex that you want to make A1 invariant, and then you build a new one, a new complex, but the way you build it is that you somehow attach, I don't know, cells, but of home intern an with value in your object, right? So if you have f, then the localization will be built out of these, I don't know, cells maybe, okay, or blocks, right? And it's somehow similar to P1 delta localization. So for P1 delta, we would get things of this form to some power. And what is missing here is really the RAM complex in the sense of foliation. Maybe tensored with something, tensored with maybe T to the some power. But then if we look closer to what is this guy here, if we evaluate at let's say at x, at smooth variety x, then we are looking at let's say étale hypercohomology maybe of x times P1 delta to some power n with value in this the RAM complex tensored with something. But now if we try to compute this étale cohomology group, what do? We will try maybe to take a hypercover of our of this variety. So we would replace maybe this by some étale cover over U. But then the group that appears will be exactly, or the cohomology of the complex that will appear will be exactly relative to the RAM cohomology of U with respect to the projection to P1 delta to some power. Right. So this is how these groups somehow appear in this formula. Okay. Right. So what we should keep in mind is that we get a formula which is nice because it's effective, but it's somehow more complicated than. I mean, of course, you see these groups are similar to that group, right? So we. So I take an étale cover of. Okay, so I erase and then so how much time I still have? 10 minutes. Okay, thank you. All right, so I try to explain now the input from Hodge theory that somehow is suitable for this problem, which I was not able really to explain completely, but let's see. All right, so yes, this is the last part. So using Hodge theory. So I need to to formulate what I was trying to say in a slightly more precise term to be able to continue. So from the theorem that I explained, that I tried to explain the meaning of it. In some sense, we get a way to express the ramp cohomology of a variety X as as a homotopy limit. Sorry, homotopy colimit. So this has to do with P1 delta localization, because it is given by some homotopy colimit of homotopy limit. This has to do with let's say hypercohomology or cohomology hypercovers. Okay, of a diagram of complexes of the form. So I write it. So the diagram of complex is a de Rham complex, but a relative de Rham complex. So it's omega dot of something that so I write x because I want to say that it depends on x. Later I will remove this from notation, but so it's a complex like this, and so it's indexed by some category which also depends on x, and so it goes to vector spaces. And so in fact really the data here is this ux plus x, and this is a diagram from a category Ix to smooth 2, and this smooth 2 is a category of morphisms. This is category of smooth morphism. So what I'm trying to say here is that for every variety X, there exists a big diagram depending on X with value in the category of relative smooth scheme, if you want. So examples, I mean, we have seen it here. Like you take U and then you project to P1 delta to some power, or P1 to some power. Right? So somehow it's maybe better to think about these guys as I don't know, as foliation, but somehow trivial foliation, in the sense that they are fibered foliations. They are given the leaves are given by fibers of homomorphism. Right, so we have this kind of diagrams, and so we look at the de Rham complex of the relative de Rham complex, and then out of this diagram we can build. So we can take homotopy limit and then homotopy colimit and get our de Rham complex, de Rham cohomology. Okay, so there is something like this. I cannot make it more precise for the moment, but it's enough to tell you what we do with this. So and then there is the following theorem. So this is where Hodge theory is used. And it says the following. So let take a diagram as before. Fix such a guy and assume the following. So there are two very important conditions. The first one is I want UI SI affine, and then I want that the projection is analytically locally trivial. All right, so it's a fibration which is analytically locally trivial. And then the important condition is that there exists a bound on the dimension of the SIs. So we assume that we are in this situation, and then I can write down the claim. Maybe put it here. So the conclusion is that then if you take the Church complex and look and truncate at degree d plus n plus 1 of this relative de Rham complex, and then you map it to the truncation just at d plus 1, sorry, then this is 0, and so it's 0 in the derived category. All right. So I don't know if you want to see the proof or not. Depending on this, I continue or I stop. The proof is not very difficult. I just I can try. I mean, I need also to clean the blackboard, right? That's the cleaning of it. Sorry? Right, you don't have a bound on n, yeah. No, you don't have a bound on n, but yeah. So this is what is missing. I mean, this is what I will not speak about today, but yeah, this is actually this is where most of the work is to reduce it to a situation where you can control the bound on. Yeah, this is. I mean, this is a crucial point of, but I won't speak about this today. So D is for every D, sorry. For every D. So as a consequence of this, one get that the homotopy limit is oh yeah, of course, the 7 is wrong. Sorry. So you have to mod out by something here, by OU. So this will tell you that the homotopy limit is actually computable, and it's given by the sheaf by the pre-sheaf OU. And there's a missing condition connected, fibers connected. I want the fibers connected. And all these are somehow can be achieved locally. All right, so here's a sketch. So what is missing in this situation is that we don't have that the complex. So this is the de Rham complex considered as a pre-sheaf on IX or I. We don't have anymore an isomorphism like this. Oops. So if you would have such an isomorphism, then in fact we can take even D plus 1 mapping to D is 0. And it's exactly the same argument as I explained using the retraction. Okay, so if we have such an isomorphism, we can project to grow 0, which is just OU, OS, sorry. Yeah, it's S, OS. And then we are done. So, but we don't have such grading because we are not anymore working with. I mean, these groups do not the relative de Rham cohomology do not form a veiled cohomology, and there is no really good theory of weight in some sense. There is a but there is no really good theory of weight. But what there is that in fact the de Rham cohomology groups are the de Rham. So these are OS modules, And in fact, they do have do have a connection, which is natural here. And these are the RAM part of a variation of mixed Hodge structure on S, maybe A. So in some sense, there is still weight, theory of weight on these groups, but it will not allow us to get such an isomorphism because there is no Tannakian formalism behind this and so on. But there is still something that you can do, which is the following. So again, this is by construction of the linear in Hodge 1 or 2. There is the following. The weight filtration has a splitting, let's say functorial splitting, after tensoring with the C infinity function on S. Right, so if we extend the scalar to C infinity function with value in C, then there is this three filtration which lives: the weight filtration, the Hodge filtration, and the opposite of the Hodge. They live there, and there is this there is a lemma by Deligne which holds for whenever you have a three compatible filtration, you can split one of them. For example, the weight filtration, you can split it, but again, it's not a canonical splitting. It's just a splitting which depends on some auxiliary choices, but with the property that it is functorial for any morphism of mixed Hodge structure or variation of this. So there is this thing, and then we can use this to deduce the claim after tensoring with C infinity S. And more precisely, we deduce the fact that we have that d plus 1 omega. Oops. So this map becomes 0, or at least mod out. So if you mod out by OS, and I should say here it's also OS linear that you have to sort of take the OS linear version. So this is 0 after tensoring with C infinity over OS. Okay, and then to get what we want from here, so to get from this to get that, we use the Dolbeault resolution, which gives something of the form O. Right. So we have a resolution of the sheaf of holomorphic function on S by C infinity, and then you go to omega 0, 1, and so on. And since there is this bound on the dimension of the basis, we see that this Dolbeault complex is of length at less than n plus 1, and by a simple argument one gets this from that. Okay, I stop here. Mm-hmm. Oh yeah, right. Okay. I mean, so yeah, you have to embed K into C, of course, and even you can assume K equals C. It doesn't really matter. I mean, for the conjecture, it does not matter. You can take K equals C from the beginning. I don't know what is exactly your question. So. Yeah, it depends on the embedding, but to get, I mean, for example, to prove the conjecture, which says that there exists a morphism to tau less than 0, this does not depend on the choice. I mean, maybe it's the construction of the map, but not even that, I think. Yeah, I mean, let's see. Maybe the construction of the map will depend on the choice, but the existence is we don't care about.